All right, guys, this is Unit 4. So we're moving into a new unit today. This is topic 4.1, which is on something called plate tectonics. You may have heard of that before. If not, don't worry about it. We're going to cover it in great detail in this particular lecture. Okay, so Unit 4 really gets into sort of the processes of the Earth. How the Earth works, so different things that cause it to change. But before we kind of get into all that stuff, I do think it's kind of important that we understand how old the Earth is, and for how old the Earth is. I mean, there's been changes that have been happening to the Earth. I think that's kind of important to put into perspective. The Earth is about 4.6 billion years old. Now, again, to kind of gauge, how old that really is, let's use a football field. So let's just say that you were standing on the goal line on one end of the field, say you're out of the Crown Point football field or something, and you walked to the other side, to the other goal line. It would take you 46 million years just to walk 1 yard. Okay, so think about how long that would take you to walk the entire length of the field. It would take you 4.6 billion years of time. So every yard, which is 3 feet, would take you 46 million years to walk. Most of this time, most of this 4.6 billion years, there's been changes to the Earth. But really none of it has involved living things, because living things really didn't come along until sort of the very end of this time frame. I mean, for example, it wouldn't be until you get within the 5 yard line of the other side of the field until dinosaurs appeared. They appeared about 225 million years ago, according to the fossil record. They went extinct about 65 million years ago. You don't have to memorize these numbers, but they're just kind of interesting. So, they went extinct about, around the 2 yard line, maybe right inside the 2 yard line. Human beings, Homo sapiens, did not appear on this planet until you get inside the 1 yard line of the other side of the field. So imagine, like, you would have to walk 99 and a half yards or so, which is almost 4.5 billion years of time, until humans even made it to the planet, even existed on this Earth. This class is partially all about, the impact that humans have on our planet. But as far as the length of time, as how old the Earth is, we have not been here this long. But the impact that we have had since we've arrived has been tremendous. And again, that's what we talk about a lot in this class, is the impact humans have had. But if you think about the age of the Earth and how long people have been here, there's really not even a comparison there. All right, so that leads us to this term, geology. You've probably heard of the term before. You've probably heard of, like a geologist, maybe, as a scientist who studies the Earth. But geology is basically the science that deals with the physical features of the Earth, the structure of the Earth, the substance of the Earth, what the Earth is made of, the processes that act on our planet to change it, the physical features of our planet. And there's basically 3 different processes, geological processes, that sort of change the Earth. And we're going to talk about all 3 of these in this unit. Number 1 is called the tectonic cycle, otherwise known as plate tectonics, which is what we'll talk about today. Number 2 is the rock cycle. That may not sound too exciting, but it actually is kind of interesting. We'll get into that more later on this week. And finally, soil formation. Soil is something that is critical to life on Earth, right? Because plants grow in soil. So if you don't have soil formation, there's a lot of living things that could not exist on this planet. It's extremely important. So we're going to talk about all 3 of these processes and how they kind of affect each other, and eventually how they shape the Earth and all the living things that survive on it. So let's talk about the tectonic cycle first, and that's kind of what our goal of today is to understand how plate tectonics works and how the tectonic cycle works. So we're going to start here with just a picture that you've probably seen before. Maybe you've not studied it before, but you're probably familiar that there are different layers of the Earth, and starting from the inside and kind of moving your way outside, we have these two inner layers. They're called the core. There's the inner core of the Earth, and there's what we call the outer core of the Earth. These two areas are extremely hot. That's one thing you probably should know about them. They're made up of a lot of different elements, but there's some radioactive elements in there that decay. You might remember from chemistry class, radioactive elements decay. And when they decay, they produce radiation, which is associated with heat. So there's a lot of heat that's generated inside of this core of the Earth, both the inner and the outer core. Now, the mantle, which is kind of this thick layer of the Earth, basically takes the brunt of all that heat. So, all of that heat produced by the core radiates outwards, and the mantle itself is basically a bunch of liquid rock because it's so hot. We call that magma. So, inside the mantle, there's a bunch of magma. It's just a bunch of melted rock. That's probably what you should know about it the most. And then finally, on the outside, we have our crust. All right, it's also known as the lithosphere, but the crust is kind of the solid outer covering of our planet. Some of the crust is above the ocean, it's above sea level, right? So that's like our continents and islands and things like that. Some of the crust is below the ocean, that would be the ocean floor. Okay, so understand that the crust can be either above water or below water depending on where it is, I suppose. All right, so just kind of be familiar with those four layers. That's really all you need to know. Now, I do want to spend a minute or two talking about the mantle, because the mantle and all of this melted rock sort of shapes the crust. All this melted rock that's in the mantle, it moves. And it actually moves in kind of a circular pattern. We call these things convection currents. Again, if you kind of remember, the core of the Earth, produces all this heat that radiates upwards. If you know anything about heat, right? Heat rises. So all that magma is rising, from the core level upwards. And as heat rises, you probably also know that it tends to cool. So as it rises, it's actually going to sink, and then it's going to kind of circulate its way around and produce these currents that flow. So we call these things convection currents, and it's basically just magma, this liquid rock that's moving upwards and then cooling and then coming down and then circulating around again. So we get these convection patterns that flow in the magma. And as that magma is moving underneath the crust, it actually is impacting the crust at the surface. So those convection currents are kind of interesting because they do impact the surface of our planet. Okay, you might be familiar with a term called Pangea. Pangea is this notion that was actually was come up with, or that actually was came up by a guy named Alfred Wegener back in 1912. And Alfred Wegener was a scientist, and he studied the Earth's processes, and he kind of understood that the continents of the planet at one time were all much closer together. And it didn't really take a genius to figure this out. If you just kind of look at the shape of the continents and how they kind of fit together like little puzzle pieces. But he was the first guy really to come up with that notion, that idea. Now, over time, the continents have drifted apart. And that's all because the continents themselves are parts of uh, t- parts of what we call tectonic plates. Tectonic plates are portions of the crust that move, all because of those magma currents that are below the surface. So, I mean, for example, millions and millions and millions of years ago, this is what Pangea looked like. It was also known as the supercontinent. But over time, those continents have moved apart, all because the plates that they're sitting on have drifted apart very slowly. So, this theory of plate tectonics is basically that these plates at the surface, the crust is made up of all these plates, they slowly drift apart, all because of those convection currents that are flowing beneath them. So, the theory of plate tectonics is the whole reason why we have earthquakes and volcanoes and things like that, which we'll talk about as well. But all of these plates, I mean, for example, we have what we call the North American plate. The North American plate, the entire continent of North America sits on it. Some of it's in the ocean, some of it is above the ocean. We have what we call the African plate, where basically the whole continent of Africa sits on top of this plate. But again, all of these plates are slowly drifting and slowly moving. Now, when I say slow, I'm talking like centimeters a year, like super slow. Like they move about as fast as your fingernails grow. So we're not talking like massive amounts of movement, but they do they do move. All right. Now, when it comes to these plates, there are three different types of basically plate movement, or plate contact, we call it. One of them is called divergent plate boundaries or divergent movement, convergent plate boundaries. Then we have something called transform plate boundaries. We're going to go through each one of these just kind of individually to kind of explain each one. So the first one is called a divergent boundary. So here, for example, is I think the picture kind of tells you exactly what happens here. In a divergent boundary, you have two plates. If you look at the direction of the arrows, these two plates are moving in opposite directions away from each other. So you got to remember what's underneath plates, right? Underneath the crust is the mantle and all that magma. So if these plates are moving apart from each other, then that magma is going to move upwards. Well, magma is basically melted rock, right? So if that magma is moving up, it's going to cool off and it's going to form new rock. So, if this is happening underneath the ocean, we call it seafloor spreading, which means literally the ocean floor is separating and then new rock is coming up and forming. This could form mountains, mountain ridges under the water. It can form mountain ridges on the surface as well. It could cause volcanic activity, which means molten lava or molten magma could come up to the surface and come out. But if it's happening under the water, it's going to cool right away. But if it's happening on land, it could come up and form some type of an active volcano. Another thing, with all of this magma moving upwards, is it brings certain elements to the surface. There's a lot of elements in that magma, things like copper and lead and iron and silver, things like that. And those things all make their way up, all because those two plates are spreading apart. So make sure we understand the direction of plate movement when whenever we have divergent plate boundaries. Now, here's another thing that could happen, especially if this happens on land. Um, Something called a rift valley can form. Here, for example, you might have two plates, one moving in this direction, one moving in this direction. And as those plates are moving, literally the earth is sinking in between. We call that a rift or a rift valley. Now, again, as those plates are separating, a lot of times what you end up getting is mountain ranges that occur on either side of the rift because the land is pushing apart, spreading, and it's forcing mountain ranges to form here. Because again, magma's moving upwards and it'll form mountains. But that rift is forming in the middle. In fact, here's a really good example. This is called the East African Rift. You'll notice this is the whole continent of Africa. Africa is a huge continent, but there's actually a rift. We call it the Rift Valley that goes all the way along the eastern side of the whole continent of Africa. There's a lot of mountain ranges in here, okay, in that East African Rift, but it literally is an area where the ground is downward. If you kind of look at this picture on the left, kind of shows you here the kind of the result of this divergence. You've got again one plate moving this way, one plate moving this way, and it forms the rift, but it also forms kind of these mountain ranges that occur on both sides of it as well. So just make sure again we know again the direction of those divergent plates as they move. They're moving in opposite directions of each other. There's also one here. I just think this is kind of something I think it's kind of important to know. This is called the Mid-Atlantic Ridge. The Mid-Atlantic Ridge basically cuts the Atlantic Ocean in half. There's two plates right underneath. Actually, there's three. There's one up top as well. But in this picture here, you're seeing the African plate and you're seeing the South American plate. And the South American plate is slowly moving in this direction. The African plate is slowly moving in this direction. Up top, you don't see it, but there's a North American plate that's also moving, to the left or moving kind of to the west. But as those plates diverge, again, under the water, you get that seafloor spreading that again forces magma up. You get a rift and you get mountain ranges that occur on the sides. So the Mid-Atlantic Ridge is basically the largest underwater mountain range that there is in the entire world. And it's all caused because of that seafloor spreading. All right, now convergent plates are just the opposite. So if you look at the direction of these arrows here, right, we've got two plates that are moving towards each other. Now, anytime this happens, you get two plates that are coming towards each other, they're going to make contact. And a lot of times, in fact, most of the time, one of the plates will slide underneath the other one. We call that subduction. All right, when one plate kind of slides under the other one. And anytime you've got plates that come in contact with each other, that could create what we call seismic activity, which is earthquake activity. So anytime you have this convergency, you get two land masses, two plates that rub into each other. This creates a great deal of pressure, and in some cases, a lot of heat that gets generated and can also possibly produce volcanoes. We'll take a look at that in a second. One of the things that usually occurs anytime you have a convergency is you get again one plate that slides under the other one, but that forces rock upwards. So typically, again, you're going to get mountain ranges that occur anywhere near a convergent plate boundary. That's a pretty common thing. I'm going to show you a quick video here dealing with something called island arcs. If you'll notice here before I play it, and there's some commentary that'll be played as well. But what you're kind of seeing here again is this subduction, right? You're going to see one plate kind of sliding under another one. Now, at the beginning of this video, it's like 2 minutes long. You're going to see how this happens when a continental plate, which is a land plate, slides into a oceanic plate, or I should say an oceanic plate slides into a continental plate. And then they're going to show you what happens when two oceanic plates come in contact with each other. They're basically the same thing, but what I want us to understand is what the result of this is. So watch this quick 2-minute video, I think it'll make a little bit of sense. I'll make some comments in a minute. Okay, I'm going to pause it right there. Again, you'll notice here that this oceanic plate is moving towards this continental plate. So let's say this is North America or Africa or wherever it is, and this is an ocean. But at the bottom of the ocean, there's crust, right? There's a plate there. So as that plate is moving towards the other one, there's subduction that occurs. This plate is kind of moving underneath the other one. And again, what this creates is a tremendous amount of heat. So you see all this heat being generated below the surface. So I'm gonna play this again. You'll kind of see the result of this. All right, so in this part of the animation, again, you're seeing two oceanic plates. But again, the same thing is happening, right? You're seeing that subduction where one plate goes underneath another one, and you get that heat that's generated. And we know the heat rises. So what this ends up creating is a series of volcanoes. Um, these volcanoes are what we call island arc volcanic islands, or we call them archipelagos. Not every single one of these volcanoes has to be active, but I want us to understand what creates them. Like, how is this island arc generated in the first place? Again, it's all because of one plate subducting under the other one, creating all that heat that rises. And once it rises, it's going to break through the surface and it's eventually going to cool and form rock. And those rocks are the islands. And those islands are basically volcanoes that could be active, could not be active. All right, so we call those island arcs or archipelagos. There's a few of them around the world that are pretty common. Here's one of the most common ones. This is called the Aleutian Arc. These are the Aleutian Islands in Alaska, and basically this is just a series of volcanoes, either active or non-active, that were formed again when two plates came in contact with each other convergently, and one slid under the other one. We actually see these arcs all over the Pacific Ocean. You see the Aleutian arc here. You've got several other ones over here in Eastern Asia, the Japan arc. The whole country of Japan basically is a whole bunch of volcanoes, active or non-active. We've got several of them here. The Philippine arc, the Indonesian arc. These are all what we call archipelagos, which again are those series of volcanoes that are formed from convergent plate boundaries that come together. Just going a little bit further with this, maybe you're familiar with this, maybe you're not. This is called the Ring of Fire. And the Ring of Fire is basically a series of volcanic or volcanoes and also earthquakes, seismic boundaries that occur all the way around the Pacific Ocean. All right, so be familiar with geographically, this region, it makes you know where the Pacific Ocean is. But this ring of fire goes all the way around. You'll notice here on the western coast of the United States, we have a lot of volcanoes, a lot of earthquake activity all the way down through the Andes Mountains of South America, again, up here through Alaska, Japan, the Philippines. This whole ring here, all right, is all because of, again, plate movement that creates volcanoes and also earthquake activity. I do want to briefly just talk about volcanoes again, like kind of what they are. Volcanoes are just basically just holes in the surface, just vents that allow magma to reach the surface. One thing I want you to know about a volcano, this is important, is that it does produce carbon dioxide. I don't care if the volcano is active or it's not active, there is natural carbon dioxide that seeps out of volcanoes and goes up into the atmosphere. That's a greenhouse gas, right? But that's been going on for millions and millions of years. These things will continue for millions and millions of years to produce carbon dioxide gas. So that's kind of a natural thing. Um, but again, we probably should be concerned not necessarily about the natural ways that CO2 goes into the air, but the unnatural or the anthropogenic ways that carbon dioxide gets up into the atmosphere. This is called a hot spot. Oops. A hot spot, I'm going to move myself over here. A hot spot is basically an area underneath the ocean, or I guess it could be on land as well, but it's an area where magma can rise and reach the surface. We call that a mantle plume. It's basically also known as a hot spot. But these hot spots, they don't move. They stay where they are. They're fixed. So, for example, these are the Hawaiian Islands. You're probably familiar with Hawaii, right? And there's several islands. There's like 6 or 7 different islands. But those Hawaiian Islands are sitting on top of a plate. It's called the Pacific Plate. Now, the Pacific Plate moves like all plates, they all move. So, for example, you see these arrows here, okay? These arrows are pointing in this direction because this plate at the surface is moving in that direction. And you'll notice that it's moving over the hot spot. So, for example, these islands over here, Kauai and Oahu and Molokai, all these islands. These are all non-active volcanoes. But at one time, these islands, these volcanoes, were on top of the hot spot because they've moved away from that hot spot. They're no longer above that area where that magma can reach the surface. Now, right now in Hawaii, there are 3 volcanoes that are actually active. One's called the island of Hawaii, the Big Island. It's on Mauna Loa. Kilauea, I don't know if I'm pronouncing that correct or not. Then there's another little island right here. These 3 are right on top, basically, of that hotspot. So if that magma does get disrupted in any way and comes up to the surface, it can come out. So if you're living here, that might be of some concern. If you're living on Oahu, you don't have to worry too much about, I guess, volcanic activity because your island is no longer above that hotspot. So I want us to understand, how that works. I mean, the Hawaiian Islands were basically formed by the Pacific Plate moving over a hotspot. So make sure we understand that. That's kind of an important thing. All right, the last type of plate movement is called a transform. Now, transform is when 2 plates kind of rub against each other like this. If you just kind of take your hands and kind of rub them back and forth, right, there's going to be heat that gets generated. So there's friction there, right? Now, this is where there's a tremendous amount of seismic activity, which is earthquake activity. Here's one of the most famous transform boundaries in the world. This is the San Andreas Fault, which is out in the western part of the United States. It actually runs right through or right next to the city of San Francisco. Los Angeles is kind of on the western coast there as well. But we call this a fault, F-A-U-L-T. A fault is basically this boundary where two plates are rubbing, next to each other. We call it a fault zone. Now, again, plates move very slowly. Again, they don't move very fast, but sometimes they move quick, like occasionally. If there's enough pressure, sometimes they'll slip. And when this happens, we get an earthquake. Now, so most of the time, that happens under the ground. Okay, this seismic activity that causes the Earth to literally shake, and when that occurs, all this energy gets released. Now, the area under the ground where this occurs is called the hypocenter. This is kind of like the exact region, under the crust of the Earth, where there's like a slippage or where there's this seismic activity that occurs. We sometimes call it the focus. But what we're mostly concerned about is not what happens under the ground. We're mainly concerned about what happens on the surface, right? Because when there's an earthquake, like buildings fall down and it gets crazy. So we call that the epicenter. The epicenter is the region on the surface that's directly above the hypocenter, where the actual earthquake occurred. So make sure we can kind of distinguish between those two terms. So again, an earthquake, it says here a sudden movement of the Earth's crust caused by a release of energy and usually causing a vibration. And most earthquakes are relatively weak. They don't cause a lot of damage. The epicenter, again, is that region on the surface that's directly above the hypocenter. But we typically measure the strength of an earthquake using something called the Richter scale. Now, the Richter scale, kind of like the pH scale, pH goes to 14, the Richter scale only goes to 10. But this is a logarithmic scale. So, for example, let's say that you have an earthquake with a magnitude of 5. And let's say we're comparing that to an earthquake with a Richter scale value of 6. A Richter scale value of 6 is 10 times stronger than a Richter scale value of 5. So if we're starting at 5 and you go to 6, that's 10 times stronger. You go to 7, it's 100 times stronger than a Richter scale value of 5. You go to 8, it's 1,000 times stronger than a Richter scale value of 5. So each time you go up a number, you're increasing the strength of that earthquake by a power of 10. Okay, so it is kind of a logarithmic scale. Again, kind of like the pH scale, if you're familiar with that. There's a couple of earthquakes that I'd like to mention that I think have some historic value, and they occurred fairly recently. The first one was an earthquake that happened in Haiti in 2010. Um, this one had a magnitude 7 on the Richter scale, so it was like the strongest earthquake of all time, but it did result in 200,000 deaths. And the reason why it resulted in so much death is basically because of where it occurred. If you look at this map here, this is a map of Haiti. And this little kind of bullseye here shows you the epicenter. And right around the epicenter is where you see the most damage done. But you'll kind of notice here that there are several cities right around this particular epicenter. And when this occurred, I mean, because it happened in an area where there's so much infrastructure, so many people, I mean, the result was catastrophic. This thing happened, and most earthquakes only last maybe 30 seconds, maybe a minute or two at most. But the damage that was done in that short amount of time was enough to kill 200,000 people. So it was, not the biggest earthquake we've ever seen, but this one resulted in a tremendous amount of loss of life. This was another one back in 2000, I believe 12. This happened in Japan. And in this particular one, the epicenter actually happened out in the ocean. It actually wasn't on land. So sometimes this will happen. Like you'll get the earthquake that occurs, out in the middle of the ocean somewhere. But usually when that happens, you get something called a tidal wave or a tsunami. So what ended up happening was a tidal wave, tsunami, that was created because of the earthquake that happened, out in the ocean. This particular wave actually crashed into the island of Japan, near a region called Fukushima. Now, the thing about Fukushima is there's a nuclear power plant that's located right on the coast. So when this tidal wave, hit this power plant, this power plant was built like back in the 50s and 60s, I think, and it wasn't built to withstand a tidal wave crashing into it. And when that tidal wave hit it, it shook the reactor core, caused an explosion, and it caused a tremendous amount of radiation to actually leak into the ocean. So, again, here's the island of Japan here, and all this big yellow blob here is basically radioactive material that was leaked into the ocean. This is how Godzilla comes to form and that type of stuff. I'm just kidding. But all this radiation is of some concern. Now it does diffuse, it does dissipate, as it spreads. But I remember when this happened back in 2012. There were scientists on the western coast of the U.S. that were measuring the water to see if this radiation had reached the United States, and they actually found out that it did. Now it was very weak, but this is not a good thing, right? To have all that radioactive material in the water, in the ocean, not a good thing. So anyway, that's it for the notes for today, guys. Here's kind of some essential knowledge that we have to know. Again, convergence, divergence, transform boundaries. Make sure we know the differences between those things. I showed you that map earlier of the Ring of Fire. You should kind of be familiar with that and just kind of know, for example, certain terminology like volcanic activity, island arcs, earthquakes, hot spots, faults. Know some of that terminology. Like if you're looking at a map, if I said, "Hey, point to an island arc," or point to an area where there's earthquake activity or hot spots, we should be able to comprehend that. All right, and then we finally talked about earthquakes as well. All right, so some essential knowledge there. Make sure we look over these notes, and I will talk to you soon. Take care.